going to go through chapter 5, 6, 7, and 9, all the key terms and vocab that you need to know. Okay? We're going to do that today. I'm going to give you some pointers on what you really need to know and should probably write down. Then I'll give you some time to work on your review packet. Chapter 5, 5.1, 5.2, and 5.3. My main question right now, we talked about this Friday, but this. Do you have this note sheet? Because I'm going to talk about 5.1, 5.2, and 5.3, but in brief. This is a lot of information, lots of great examples that I would highly, highly, highly recommend you have. However, like I said, I'm not going to go over this all in detail because you should have this, and I've done this like twice already this trimester. So find that. That'll be beneficial. But for right now, let's talk here. If I say, hey, here is a triangle, how do we draw in the midsegment? How do we find the midsegment? Yeah, find the middle of this side so that this part is congruent to that one. Find the middle here so that those parts are congruent, and then we can connect them. That's one midsegment. I could draw in at least two more. Okay? Okay, so if this is the midsegment, let's say this is 6 units. How big is this one? 12. So if midsegments, we know one is half as big as the other, or one's twice as big as the other, right? What else do we know about these two? These two segments are, what do we know about these two segments? The midsegment is parallel to the other side, right? Those two segments are parallel, one's half as big as the other, and again, all that information is right on that 3-column chart. Okay? We're talking about it in brief right now. What's this word equidistant mean? Equal distance. They're the same distance, right? Same distance, equal distance, yep. If I say concurrent, these lines are concurrent, these rays are concurrent, these planes are concurrent, what's concurrent mean? Or what's point of concurrency mean? Where they meet. Yeah, and if we talk geometrically with geometry terms, where they meet, that's called, starts with an I, the intersection, right? If I say these lines are concurrent, that means they intersect. It's like the point of intersection. So I say, what's the point of concurrency of perpendicular bisectors? Where do perpendicular bisectors intersect? Perpendicular bisectors intersect at our circumcenter. We have something called a circumcenter. Let's talk first of all, what's perpendicular mean? Two lines intersect at 90 degrees. And we have this cool symbol in here that sometimes appears. This is a symbol for perpendicular, means they intersect at 90 degrees, and bisector means splits it in half, splits it into two equal parts, right? So, I give you a triangle that looks like this. It's a right triangle, and I draw the perpendicular bisector. It bisects the side, so I find the middle, and it's perpendicular, right? Intersects a 90-degree angle. I find the middle of this side. I draw my perpendicular bisector. Look at that. I find the middle of this side. Oh. That place they all intersect in the right triangle is actually on it. And so this place those three all intersect is called our circumcenter. The place where three perpendicular bisectors intersect is called your circumcenter. And we know the circumcenter is the same distance to the vertices. Somebody's got their notes, or somebody remembers. It's the same distance to the vertices. And what's a vertex? What's a vertex? The angles, right? Like your corners. So this point is the same distance to this corner as it is to this corner as it is to that corner. And angle bisectors intersect at the incenter. So I have this triangle. I bisect this angle so that those are equal. I bisect this angle so that these are equal. I bisect this angle so that these are equal. In this place they all intersect is called our incenter. And the incenter is the same distance to the sides. This one's to the vertices, this one's to the sides. chapter 6, we talked about, it was like all about ratios and proportions. 6:1 to 6:6 is like the same thing over and over and over again is what it seemed like. If I say a ratio, what's an example of a ratio? 3 to 1, 1 to 2, 2 to 4. How's 2 to 4 simplify? 1/2, right? And we went in and we simplified all these ratios. And we also talked about proportions. A proportion is like x over 3 equals 6 over 9. How do you solve it? Cross multiply. You guys can do that. Geometric mean. Find the geometric mean of 16 and 3. This says find the geometric mean of 16 and 3. We first of all need to know how to set it up. So, geometric mean means we're solving for the means. You have your extremes and you have your means. So our x's are on the means. And then you've got your 16 and your 3. How do we solve it? Cross multiply. X times x, x squared. 16 times 3, 48. How do we get rid of a squared? Square root, and I type it in my calculator, and square root of 48 gives me a decimal. If I have 1 squared, that is 1. 2 squared is 4. I'd probably put these on my paper, right?
Yeah.
4 okay. But you gotta have these down so you can type them in your calculator quick and go through, and 7 squared is 49. 8 squared, 64, 9 squared, 81, 10 squared, 100. If we had to go higher, we could go higher. So, we go through the list and they're like, well, what goes into 48? Where does 48 fit? 48 fits like right in here. 48 divided by 36? No. 48 divided by 25? 48 divided by 16? Yeah, it's kind of a dead giveaway because that's the numbers we started with. 16 goes in it 3 times. 16 times 3 gives us 48. Which one simplifies?
16.
Gives us 4 square root of 3. There's your answer. When we talk about scales and scale drawings, an example of a scale on a map is like 1 inch represents 4 miles, 500 miles, right? So it's like, it's always like the 1 inch, the 1 centimeter, the small unit. So it's like your model over actual, yep. A scale is always the model over the actual. And when we find scale factor, what do I do to find scale factor? We compare two corresponding sides. Compare two corresponding sides. So here's an example. We have a rectangle. This side is 20. That side's 10. So when I say find the scale factor, I'm not telling you which one we want to start with. The sides that match up, this one corresponds to this one. So we have 20 to 10, and it simplifies 2 to 1. Similar figures versus congruent figures. This is a very good question that you need to know. Similar figures versus congruent figures. What's similar mean? Corresponding angles are congruent, corresponding sides are proportional. Corresponding angles are congruent, corresponding sides are proportional. So check this out. If I give you a square, oh, it should look like a square. 4 right angles, and all 4 sides are the same, so maybe we have 14, 14, 14, and 14. And then I have this one. So look, are those similar? Why? Corresponding angles are congruent, and my sides are proportional. 14 to 7, 14 to 7, 14 to 7, and 14 to 7. All the sides are proportional. Congruent figures. What would congruent mean? They're the same. Equal. Everything's exactly the same. All the angles are equal, and all the sides are equal. So with congruent figures, we say corresponding angles are congruent. Corresponding sides are what? Congruent. So congruent figures, everything's congruent. So check this out. Let's go 30 degrees, 60 degrees, and 90 degrees. It's a 30, 60, 90 triangle, isn't it? 30, 60, 90. The angles are congruent. The sides also must be congruent if they're congruent figures. So if this is 7, this is 14, and this one is 7 square root of 3. 7, 14, 7 square root of 3. They're congruent because everything is exactly the same. Sides are the same, angles are the same. Chapter 7. Pythagorean theorem. What's the Pythagorean theorem say? Yeah, I like it too. I like the trig better, but I like that. C is always, which is exactly right. The hypotenuse is always the longest side. And so, Pythagorean theorem only works with a right triangle. It's got to have a right angle in it. So here's our right angle. That makes this our C value. That's always the hypotenuse across from the right angle. Triangles. If I say, classify this triangle as acute, right, or obtuse, we have to use this rule. C squared question mark A squared plus B squared. That tells us if it's acute, right, or obtuse. If it's an acute triangle, it is less than. If it's right, it's equals, good burn. And if it's greater than, it's obtuse. Obtuse is greater than, it's like it's big. 6, 11, and 8. So what goes first? 11 squared question mark 6 squared plus 8 squared. 121 is greater than 100. So because it's greater than, it is obtuse. It's an obtuse triangle. SOHCAHTOA. Some of you would prefer to see it written this way just because it kind of makes it easier to know what's over what. Sine is opposite over hypotenuse. C is cosine, which is
adjacent over hypotenuse.
Adjacent over hypotenuse, and T is
opposite.
Angle of elevation and angle of depression, I'm not too concerned about, but just remember this. If angle of elevation is like what you look up at, the angle you look up at, and angle of depression, it's depressing, so from looking straight ahead, you look down. It's the angle that you look down at. That's right. To solve a right triangle, you need to do two things. What's one of those things? Find all sides, and what else? Find all angles. To find all the sides, to find all the angles, we have a couple different routes we can go here. If I say, let's start with the angles, how many degrees in a triangle? 180. So we know all angles add or equal 180 degrees. So you can add the two, subtract from 180, that'll get you your third. We can also use sine inverse, cosine inverse, and tangent inverse. And again, that inverse is what you have to use for angles. For sides, we we can use sine, cosine, and tangent, just the regular. But first let's talk about a squared plus b squared equals c squared. That'll help you find sides. And again, also use sine, cosine, and tangent. In chapter 6, to find side lengths, we did this. We write a proportion as another option. So maybe if I give you triangle that looks like this, triangle that looks like this, let's go x, 15, 20, and 4. What would your proportion look like to solve for x? Let's go this way. X compares to 15 and 4 over 20. And then you can cross multiply. And then, last but not least, how about those other rules? We had 2 different sets of rules for the special triangles. Remember the 45, 45, 90? We had the 45, 45, 90, and we also had your 30, 60, 90 degree rules. With 45, 45, 90 triangles, something that looks like this. 2 legs will be the same. So this is a leg, this is a leg, this is our hypotenuse. And often, some of you know the pattern. You're like, hey, if this is 5, this other leg has to be 5, and that means the hypotenuse is 5 square root of 2. Some of you get that. Others of you would prefer to use the rule. The rule for the hypotenuse says leg times the square root of 2. And then we also have a rule for the leg. Leg equals hypotenuse divided by square root of 2. We also have your 30, 60, 90 rules, which looks like this. 30 degrees, 60 degrees, and your 90 degree angle. This would be our hypotenuse. You have a short leg, and you also have a long leg. If I say, hey, the short leg is 8, that means the hypotenuse is 16, and the long leg is 8 square root of 3. Again, some of you know those rules. You got it memorized. You're like, I just know how that works. Others of you would prefer to see this written. Hypotenuse equals short leg times 2. Long leg equals short leg times the square root of 3. Short leg equals hypotenuse divided by 2. And the other one, we have short leg equals long leg divided by square root of 3. Chapter 7. We got chapter 7. Chapter 9. Chapter 9. Chapter 9, this is what we just touched on. This is what we left off on. This will go pretty quick. We have image and we have pre-image. Image is always it's the new one, right? It's the one that comes after. It's the new figure. Pre-image is the original one, or the first one we start with. Image is the A prime, the B prime, the C prime, the A prime, the B prime, the C prime. Usually those are the ones that are dotted. And then the original is like your A, your B, and your C. And so all these terms, the image and the pre-image, those apply to all our transformations. So that's like the big overarching word is a transformation when we do something to a figure. And so we talked about this word isometry too. What's isometry? We keep the side lengths and angle measures the same. So when I translate something and I keep all the side lengths and keep all the angle measures the same, a translation is in isometry. The translation is in isometry. Same as a reflection. When I take something and I flip it over, I still keep the side lengths, I still keep the angle measures the same. Same with the rotation. Is a dilation an isometry? No. A dilation is when we stretch or shrink something. Rotation, you have 3 rules. If I rotate 90 degrees, AB turns into negative BA. 180, AB becomes negative A, negative B. In 270, AB turns into B negative A. And so like we said, dilation is either like we stretch it or we shrink it. And specifically, that's where we started talking about enlargements and reductions. If it's an enlargement, the scale factor is greater than 1. If it's a reduction, yeah, the scale factor is between 0 and 1. And lastly, what's the rule for scale factor? Always, always, always image over pre. Sweet! That's all the terms.